We begin chapter 16 with a throwback to a concept from a long time ago, potential energy. You recall that potential energy is the energy stored in something. You can have gravitational potential energy. You can have the potential energy stored in a spring. You can even have the potential energy that's stored in the bonds of molecules, chemical potential energy. And in this particular context, potential energy is considered a conservative force. Now that also is a throwback to an earlier chapter, chapter 5. A conservative force, as opposed to a non-conservative force, is a force that it doesn't matter how you get from point A to point B. For example, you could climb up a mountain and take any one of a dozen different routes, but if you start in the same place and you end in the same place, your total potential energy that you now have is going to be the same. There are lots of things that are conservative like that. When it does depend upon the path, whether you take a rather circuitous route to the top of the mountain or you go straight up, the big difference is going to be the amount of friction that you encounter. And whenever you have friction involved or friction as a factor, then you have a non-conservative force as opposed to a conservative force. And you'll see that come up in other places as well. In chemistry, we often talk about chemical reactions that doesn't matter how you get from reactants to products. There could be multiple different ways. The total net energy is the same. And we talked about a state function like that. Now, in this particular chapter, we're going to be defining a term called electrical potential. And when we define this term, it's the potential energy per unit charge. And the potential energy per unit charge, we're going to learn, is sometimes called the volt. A very important term in our unit on electricity and magnetism. And we're also going to be introducing later in this chapter electrical circuits, and then a particular device for storing electrical energy called a capacitor. So, electric potential energy versus electric potential. These two terms do not mean the same thing. The electrical potential energy is going to be like all forms of energy, measured in joules. But the electric potential is going to be in terms of units, is going to be joules per coulomb, or work per unit charge. And that's the breakdown definition of what a volt is. A volt is not a measure of electrical potential energy. It is a measure of the electrical potential energy per charge, and that's called electric potential. It's important to keep that distinction in mind. Now, in this diagram over here, we have two metal plates, and as is our convention, we draw our electrical field lines representing the strength of our electrical field going from the positive to the negative. And in this particular diagram, you'll notice that we have a positive charge right there. And as it is in the electrical field is going to act on that positive charge, and the positive charge is going to move from the left towards the right. Now, there are a number of different ways we can think about this. One is that because the charge is positive, and this metal plate over here is negative, opposites attract, and the positive charge is going to go towards the negative metal plate. Another way of looking at it is that when you put a positive charge in an electrical field, it's going to move in the direction of the electrical field, of those flux lines that you have drawn, the arrows here, which are representing the strength of the electrical field. And it's going to move with that field, again, from the left to the right. In a sense, we could say that if we were to turn this upside down, and we were to have our two metal plates, one on top of the other, and with the arrows going in this way, from the positive to the negative, It's analogous to gravity. If I have an object, a mass way up here, it's going to be acted on by the gravitational field, and it's going to move in the direction of the Earth. So there is an analogy between gravitational fields and electrical fields when you set them up correctly. So just like the gravitational force, being an inverse square law, is a conservative force, so is the electrical field. And the Coulombic force of a charged particle in the electrical field, a conservative force. This means that in the case of gravity, if we come back to the diagram down here, if I have an object, a mass that I move up in one direction, and then I move it back down, then I move it higher, and I move it lower, and then higher, and then eventually I move it down, the net change going from here to there is the same as if I just dropped it from there and it went to there. It doesn't matter how many times I go up and down. The net change in potential energy is the same. So the gravitational force is conservative. The Coulombic force is conservative. If I have a positive charge and I move it down, push it back up, move it back, let it move back down, push it back up, and eventually let it move back down again, the net change is going to be the same. Remember, electrical field strength is defined as the electrical force per unit charge. And when we multiply both sides by Q, we get F equals the electrical field strength times Q. And if we remember that work equals force times distance, Q times the electrical field, here's my force, and here's my change in distance. So work equals force times distance, and in terms of electrical fields, we can say that work equals the magnitude of the charge moving in an electrical field with strength E through a distance from one final spot resulting from where it began at some initial spot. Now this formula right here, work equals QED, is a nice, easy, quick way of thinking about the work done on or by a charged particle in an electrical field. But the one problem with this particular configuration is there is no negative sign. It doesn't remind you of the correct convention. It doesn't indicate whether the electrical field is doing work on the charge or some outside force is doing work on that charge. One would be exothermic, if you will, work going into the system. One would be endo, going into the system would be endo, and coming out of the system would be exo. So when we come down here, when we do work on a charged particle in an electrical field, and here's the magnitude of the work, if we're doing work against the electrical field, moving a charged particle against the direction that it naturally would want to go, and then we let go of it, it's going to move back again and exhibit a certain amount of kinetic energy. So we can convert the potential energy stored in the charged particle as a result of the work we've done on it, moving it against the electrical field, and now that charged particle is going to move on its own spontaneously, and it's going to pick up velocity and have a certain change in kinetic energy as it moves with the electrical field. Now, coming down here to this more accurate configuration, we throw in the negative sign now to indicate whether or not the charged particle is having work done on it, or whether that charged particle is acting under the influence of the electrical field itself. And again, our unit of work is the joule. So the change in electrical potential energy of a system consisting of an object, and I'm reading up here, with charge Q moving through a certain distance, delta X, in an electrical field is given by this. And you can see it's potential energy is becoming less and less as it moves under the influence of that electrical field. Now, if I were to exert a force on the charged particle, and let's say this is my positively charged particle, here is the negative, and up here is the positive, and the electrical field is going this way. If I'm moving this particle up against the electrical field and doing work on it, I'm increasing the potential energy that the charged particle now has. Notice that the way we've been drawing these arrows between two metal plates, or even, they don't have to be metal plates, they're just charged, they can be non-conductors that have a static charge. There's an electrical field between them. Notice that my electrical field is uniform. Unlike having a charged object, where if you think about arrows going out, the farther and farther away you get from Q, if I get way out here, my electrical field strength is a whole lot less than my electrical field strength right there. And so we would say that the electrical field is not uniform. And so if we're going to use the equation that the amount of work being done, or the amount of work that can be done by a charged particle in an electrical field, we want to, and we're just looking at it, not necessarily whether the charged particle is having work done on it or the charged particle is acting spontaneously under the influence of the electrical field. The magnitude without the sign is the absolute value of that charge times the electrical field strength times the distance in that electrical field that the charged particle is moving. And so here's a picture that shows a comparison between the gravitational field and the electrical field. So imagine that I've drawn here a line that I'm going to call sea level. And so I have an object up here that is above sea level. It has a certain amount of potential energy relative to sea level. If it is below sea level, we'd have to do work on it to get it back up to sea level. Or if I have a charged particle down here near the Earth and I want to move it against the gravitational field, I have to do work on it. So in some cases, I'm doing a positive amount of work, and in other cases, the work that's being done on it is by the electrical field, and the amount of energy that the particle now has on it becomes less and less as the particle goes in the direction that the electrical field would naturally want to take it. And we can do the same thing over on this side now. Imagine I have a charged particle here, and this is a positive test charge, so it's positive. It naturally wants to go with the electrical field, which is going from the positive to the negative, the convention for all arrows, okay? And again, imagine that this is where it would end up with having 0 potential energy per charge. Imagine somehow it could go through the surface and end up down here. Then it would again increase in potential energy, and it would have to go back to get to that equilibrium position. Or imagine I had a particle right here, positively charged particle. I'd have to do work on it to move it away from sea level, away from this metal plate right here, positive to negative. And that would be an increase in the work I'm doing on the charged particle. Over here, as the charged particle naturally moves with the electrical field, it has less and less potential energy in it until it goes to 0 at this particular point. So you can see the analogy between the two. So once again, electric potential energy differs significantly from gravitational potential energy because electrical charges can have positive and negative, and at least as far as we know, gravity is always positive. We don't have any anti-gravity particles or anti-gravity fields, though as we investigate this thing called dark energy, we might come to different conclusions at some point in time. And once again, just like we were using the work energy theorem way back in chapter 5 and 6. In that work energy theory, all the work and energy that we had before some point would equal all the work and energy after some point in a word problem that we were pursuing. For example, thinking of a car coming down an inclined plane, going across the plane, maybe striking a barrier with a spring, or maybe going up an incline. We could talk about all the energy it has at the top compared to all the energy at the bottom, compared to all the energy at some other point. And we'd use the work energy theory so that the total amount of work energy at any place along the problem is going to be a constant. And we can do the same thing here. The total change in kinetic energy plus the total change in potential energy will always be a constant. And so when we look at this first problem here, we have a proton, positively charged particle. It's released from rest at a position of -2 centimeters. And we have a constant electrical field, which would probably imply two surfaces with the same electrical field all the way through, as opposed to some sphere that would have electrical field that would change as you got farther and farther away from it. So I'm going to erase that, because that's not what we're looking at. And then in part B of the problem, we're going to talk about an electron instead of a proton. Also notice that my electrical field has this force per charge. Remember, force per charge, or Newton per Coulomb, is not a volt. A volt is a work per unit charge, a joule per unit charge, not a Newton per unit charge. So when we're looking at electrical field strength right here, we're not talking about volts, which is a term that most physics students have heard many, many times. Just needed a drink of water there. And then in part C of the problem, we're going to reverse the electrical field. So what I've done here is attempted to draw an electrical field going from positive to negative. And notice my arrow by convention is moving from positive to negative. And I've designated some positions as well. Position of -2, 0, and +5. And so if I'm starting with my proton at position -2, and it's going to move with the electrical field, so the electrical field is doing work on my positive charge, moving it spontaneously naturally in this direction. When we go to use our formula, my change in potential energy is going to be QED, where Q is going to be the charge of the proton, which is an equal and opposite to the charge of an electron. So that's a positive charge. The strength of my electrical field was given to me in the problem. My change in distance, my final position is 5 centimeters. My initial position was a -2 centimeters. Notice that I had to convert centimeters into meters because I'm working with joules and I'm working with newtons. This is something that is often forgotten by physics students, to convert your distances into meters. Now the negative sign here is because my potential energy is diminishing as my positive particle gets closer and closer to the other end, to the negative end of the field. I have less and less potential energy. My electrical field is doing work on my charge. Now, in part B, we have a negatively charged particle. And my electrical field is going in the same direction. And so now I have to do work on the charge, because the charge is not naturally going to want to go from negative with the electrical field towards negative. It actually would naturally want to go that way towards the left. So I have to do work on it. That's going to give me a positive value here. And again, I'm going to be going my net change is my final position is position 12 centimeters, which is 0.120 meters. My initial position was the same as the protons at 2 centimeters, or 0.020 meters. My electrical field strength hasn't changed, but now I have a negative charge because it's an electron and not a proton. And now the work being done is positive because instead of the electrical field doing work on my positive proton, an outside force has to do work on my negatively charged particle to move it in a direction against the electrical field. An analogy would be if I have a mass sitting on the earth and I want to raise it in the direction it doesn't spontaneously want to go, which is off the earth, I have to do work on it. And as I do work on it, equaling to mgh, I'm going to end up with a particle up here with a positive amount of potential energy in it. And then in part C of this problem, we reverse the electrical field, so it's negative there, it's positive there. And as we move from position 3 to position 7, according to the problem, 3 centimeters to 7 centimeters, which is going to look like this when we convert it into meters. Again, we have a negative electron with that magnitude of charge. Notice my electrical field, since I reversed it, is now a negative sign there. And because my negative charge is moving with the electrical field, it naturally wants to go towards the positive. Therefore, I have a negative sign there. We are not doing work on the electrical charge, but the electrical charge is responding spontaneously to being in the electrical field. So that's given a negative value, and here you got to be careful. We have a negative sign there, we have a negative sign there, we have a negative sign there, and we end up here with a negative amount of work. All right, let's look at another problem here. Using electrical potential energy in a conservation of energy problem. So this time we have the speed of a proton. It's at this position. It's already converted to meters for us. It's referring to the previous example at the top of the page. And we want to find the initial speed of an electron in part B as opposed to the speed of a proton in part A. When the speed has fallen by half, when it reaches this position right there. In other words, my final velocity in this part of the problem will be 1/2 of my initial velocity. So we come over to the top of the next page, and we say that all of my kinetic energy is going to cause a reduction in potential energy as my proton moves spontaneously in the direction that it would naturally go in this electrical field. And so we can say my kinetic energy, which is 1/2 mv squared, and my potential energy, which is going to be right here. We're going to solve for that potential energy. So we're going to leave it as potential energy. Well, we're given that, if I remember correctly. We're given the potential energy back on the previous page. That's right. In the previously solved problem, excuse me. So we're going to solve this equation for V, which means we're going to multiply both sides by 2, which is going to get the 1/2 to cancel out. And we're going to divide both sides by M, which is going to put M in the denominator So there's my 2 when I multiply by 2. There's my M in the denominator when I divide by 2. My negative sign, which was right there. And now we're going to take the square root of both sides and solve for my velocity. And there's my speed. And then we're going to do a similar kind of problem where we have a change in kinetic energy, but that change is not down to 0 kinetic energy, but it's down to half the speed that I had before. And so when you take 1/2 of 1/2 of 1/2 squared, you get 1/8. And over here, 1/2 is the same as 4/8. So 1/2 of 1/2 squared gives me 1/8, minus 4/8 gives me my negative 3/8. And again, we solve for my velocity by multiplying by 8/3 and dividing by mass. And now you notice my speed is much greater. In fact, we're closing in on 10 to the 7th meters per second. And of course, 10 to the 8th meters per second, 3 times 10 to the 8th meters per second is the speed of light. So we would almost get in the vicinity of having to worry about the relativistic, some relativistic changes. And notice the electron goes a whole lot faster than the proton because the electron is much, much lighter. Now back to electrical potential. Electrical potential, you'll recall, is going to be the work per unit charge. The work per unit charge. And that work per unit charge, right here, is also known as the volt. And if my work is my potential energy, of course, is measured in joules, charge is in coulombs, and a joule per coulomb is the same thing as a volt. And when we talk about the electric potential difference, let's say from the positive post of a battery to the negative post of a battery, whether it's a car battery or a AAA battery or a D battery or whatever, that potential energy difference is measured in volts. The potential to do work per charge. And that electrical potential is a scalar quantity. There we go. It's a scalar quantity. And it also means that, well, when we do 1 joule of work to move a 1 coulomb charge, we're going to get, it's going to be the equivalent of 1 volt. From the definition of 1 joule of work must be done to move 1 coulomb of charge between 2 points that have a potential difference of 1 volt. And again, if you remember that work is force times distance, and if you also remember that force over here is going to be equal to electrical field strength times charge, and so we substitute that in for E and divide both sides by Q. My work per charge is known as a volt, and that work is my potential energy per charge, and it's going to equal E. Here's my E, force divided by charge, and X is my distance. So my change in voltage is going to be equivalent to my electrical field strength times my change in position. And again, the negative sign depends upon whether the charged particle is moving spontaneously, naturally within the electrical field, or you're doing work on that charged particle to move it against the electrical field. And notice then that the units of a Newton per coulomb are the same thing as a volt per meter. Newton per coulomb is the same thing as a volt per meter. And I'll let you do this quick quiz. I gave you some of the answers, so you didn't have to look them up in the back of the book, okay? And let's come over here to the top of the page. When you have a charged particle and it's moving under the influence of electrical field, let's say through a circuit in a battery. So let's suppose that this is my battery right here, and the little knob there is the positive end of the battery. There's the negative end of the battery, and we have a wire coming out of the positive end, and I'm going to make a zigzag symbol there and a wire coming back to the negative end. And this zigzag is some resistance R, which you'll learn more about in the next chapter. And this resistance could be a light bulb or a buzzer or your calculator or whatever it is that needs electricity in order to recharge it, or electricity in order for it to operate and do work for us, whether that work is sound or light or heat or anything else. By convention, we always say that my charge goes from the positive to the negative. Very important, from the positive to the negative. It always uses up its energy in the circuit. And then when it gets back home again to the negative end, it now has 0 electrical energy per charge. It goes from the maximum electrical potential energy per charge that the battery is capable of giving it. If it's a brand new 9-volt battery, then that would be 9 volts. If it's an older 9-volt battery that's been used for a while, it might be down to 8 volts or 7.5. But whatever that energy per charge is, that voltage is, it has that maximum value to start with, and it always returns home again with 0 voltage. And I've invented this little phrase here, PTO. The charge always returns plumb-tuckered out. PTO, plumb-tuckered out. Little southern talk there. Now, of course, if I have a much bigger resistor, then not as much charge is going to be able to be pushed through it. And if I didn't have a resistor at all, so if I were to erase that resistance, and if I just had a wire like this with no resistor in it, that would be a short circuit. And that short circuit would mean all of my energy has to be used up in the wire, which would heat it up. And that would also mean that my battery might also kind of heat up because it's trying to push an infinite amount of charge through a wire with 0 resistance. That would be a short circuit. Now, example 16.3, TV tubes and atom smashers. These are the old-fashioned TV tubes. You might remember, if I can try to draw an old-fashioned tube, if this is the face of the tube, and then it kind of came back down here, okay? And it had a narrower ending here. And in the back here is where you have a high voltage source, and it shoots a beam of electron towards the phosphors, and the phosphors would coat the screen of this tube and cause those phosphors to light up and produce an image on this tube. These old-fashioned TVs were heavy. They took up an awful lot of space, and you don't even see them anymore. The town that I had to drive through when I went from Rexburg, Idaho, where I would live during the summer with my family, down to Idaho Falls, where my research lab was, that town was very, very small, called Rigby, Idaho. And in Rigby, Idaho, they had a museum to Philo T. Farnsworth, who was one of the inventors of this tube over here, sometimes called a cathode ray tube, because the cathode was the device at the bottom from which these negative charged particles, the electrons, beam would emanate. Now, in any case, that's a little background. So one of these days, these problems might not even be in the more modern edition of the book, because students won't necessarily know what people are talking about. But this is the way that we speed up charged particles in cyclotrons and accelerators. We make them go faster and faster by pushing them out of a positively charged metal plate through this opening and attracting them towards a negatively charged plate. And as my particle exits the negatively charged plate, we immediately, using alternating current, turn this negative plate positive, and we have another negative plate farther to the right, which is now negatively charged. And so my charged particle starting here accelerates. We reverse the charge on this positive negative plate, make it positive, and we accelerate it some more through another hole. And we just keep doing this over and over and over through many charged plates with holes in it until my charged particle is moving it at near relativistic speeds, in this case 3 million meters per second. And that's how we accelerate these particles. In any case, when we look at this problem, we want to find the electric potential that's going to give me the desired speed. And so we have the initial kinetic energy of my particle, and it enters an electrical field right here. And it's going to have some final velocity as a result. And so when we look at the math, when we accelerate it, there is a QV over here that's 0. So we have my particle already has kinetic energy. Now it's going to pick up more energy by being in the electrical field. And when we finally reach the destination, and it's no longer in that electrical field, it has some terminal velocity. It's going to have more kinetic energy than it had before. So here's my change in kinetic energy from start to finish. And here is here's the charged particle itself. And we're going to solve this equation for the velocity by plugging all my numbers in. And you can see then what my change in speed is going to be. Well, first of all, I said that all backwards, I think. This part here is my change in velocity, not my change in, this got my V's mixed up. This is change in voltage. This is my change in velocity. We're plugging in the changes in velocity, and we're going to get the change in the potential energy per charge, which is the voltage, which is why we took my change in energy, and we're dividing it by charge to get my voltage. Change in energy, of course, is joule. Change in charge is coulombs, and a joule per coulomb is my change in voltage. So my change in voltage is this much. This is how much work was done in accelerating this particle in the electrical field. Now, at this point, I'm going to stop the broadcast, and we will pick this up in the next screencast.